Carbon-13 NMR on its own is not as useful as proton NMR. In fact, it's most often used in addition to a proton NMR to help you figure out a structure. Most of the problems we work with in this class can be solved using just a proton NMR, but sometimes a carbon NMR will be provided to you as an extra bit of information. Now, the reason that carbon NMR is not as useful as proton NMR is because it only tells us two things: the number of signals, so the number of different types of carbons in a molecule, and the chemical shift. Now, the reason that carbon NMR does not participate in multiplicity or splitting is because the hydrogen-carbon splitting is often so complex that the spectrum is unreadable. So to make a carbon NMR data actually easier to read, carbon NMRs are often decoupled. And decoupled means we take away the magnetic effect of the neighboring hydrogens and focus solely on the electronic environments of the carbon atoms. So down here we have an example of a carbon NMR. You'll notice that we have varying chemical shifts from about 0 to 200 ppm. The peaks are shown as spikes. They are not split, and you'll always see just solid spikes. In general, we count the number of peaks to help us figure out how many different types of carbons we have in the molecule. As far as the chemical shifts in carbon NMR, whenever we're working with sp3 hybridized carbons, they tend to come out at the lowest ppm. They are the most shielded types of carbon atoms. Next, we have sp hybridized carbon atoms as well as sp3 hybridized carbon atoms that are attached to electronegative atoms. Those electronegative atoms as well as the sp hybridization increase the chemical shift to about 50 to 100 ppm. From 100 to 150, we have all sp2 hybridized carbons. And then in our last set, our highest chemical shift usually goes to carbonyl carbons that are double bound to an oxygen atom. These carbon atoms are highly deshielded, therefore have the highest chemical shift. Determining the number of signals we would expect to find in a carbon NMR is the same as with proton NMR. So we're looking at carbons that have different stories or different descriptions. If they have a different story, then it means that it will give a different signal. Now in these examples, we have symmetry involved in the molecules. Symmetry can help us determine the number of signals by drawing a line through the symmetrical portion. So here we have this molecule and we have a line of symmetry right through the middle. Now because we have symmetry here, we can just focus on one side of the line of symmetry. So we have 1, 2, 3, 4 carbons, which all have different stories. This is a methyl group. Now, because we have symmetry, this methyl group is identical. Then we have the carbon attached to the methyl group. Then we're going further away from the methyl group. And finally, we're at the carbon furthest away. So we have 4 different signals representing the 4 carbons in this molecule. With this one, the line of symmetry is straight through the middle. Now we're going to consider all of the carbons on one side of that line of symmetry, as well as any carbons that go through that line of symmetry. So in this case, we have 1, 2, 3, 4, 5 different carbons, which would give rise to 5 different signals. In this molecule, we have 2 lines of symmetry, one straight through the middle here, and one through the middle here. Whenever there's 2 lines of symmetry, we're going to consider one quadrant. So any carbons that lie within one of the quadrants or on one of those quadrants. So we'll focus on this upper left quadrant here. We have a carbon and 2 carbons on the line. So we have a total of 3 signals in this molecule. So for this example down here, how many carbon signals would we expect to find? Well, first let's look for lines of symmetry. Now we have a line of symmetry straight through the middle. We also have another line through the middle of our 2 carbonyls. So this part of the molecule is reflected exactly on this side. So again, focusing on the carbons in one of the quadrants, and we'll focus on this top left quadrant here. We have 1 carbon that is on the line, and 1 carbon that is off the line within that quadrant. So we have a total of 2 carbons, which would give rise to 2 signals. Now there's a more complex type of carbon NMR known as distortionless enhancement by polarization transfer NMR. This type of carbon NMR provides information about the number of hydrogen atoms that are attached to each carbon. So what we've just been talking about is full decoupled carbon NMR. Now this type of NMR shows all carbon peaks. Now there's 2 types of the DEPT NMR. DEPT 90 only shows CH signals, so carbons that are bound to 1 hydrogen only. DEPT 135 gives different types of signals. For CH3s and CHs, it gives a positive signal, so that means that the peak is going to appear above the x-axis. If there's CH2s present in the molecule, it gives a negative signal, meaning the peak comes below the x-axis. Many times, these 3 types of NMR are used with one another, along with a proton NMR. Now again, our broadband decoupled carbon NMR shows all types of peaks for all types of carbons. For the DEPT 90, it's only going to focus on CHs. And for the DEPT 135, we get the up signals for the CH3s and the CHs, and down signals for the CH2s. The DEPT 135 does not show any signal for a carbon that is not bound to a hydrogen. So again, all of these can be used with one another, and sometimes they are provided along with the proton NMR. For the purposes of this class, you can use this information if you would like to, however, it's not going to be a requirement.